Hi, today we'll talk about information theory. Okay, we will understand what information means and how do we kind of use it in machine learning and data science. Okay, let's start with a simple example. Uh, so, I live in Chennai, okay, a city in India. Okay, it's it's 90% sunny here. Of the entire year, it's 90% sunny, and 10% probably it rains. Okay, that's mostly the weather. Okay, it rains and it's sunny. Just assume that there are only two weather, and mostly it is sunny. Okay, this is the rains. If someone comes and tells to me that okay, it is going to be sunny here, I'll be like, oh yeah, that's how it is. There is no surprise, right? It's how it is. And someone tells me that it is going to snow in Chennai. Okay, then I'll be like, what? Does it ever happen, or is it even possible? Okay, that creates more surprise and excitement. So anything which you know for sure and take it for granted is always having less surprise. Anything which is like very rare or like extreme will have a lot of information. But anything which is like out of normal will have little bit of surprise. But sometimes it rains all of a sudden due to some change in the weather pattern. Then it's a surprise. Okay, it's a little bit of surprise. If it snows, it never happens here, so it is extremely rare. Even it's like completely blow out of proportion, and it'll even surprise us. So the idea of information is closely related to the surprise actually. So when you say 90% sunny, the probability of rain being sunny is 0.9. When it says it's going to rain, the probability of rain is going to be 10%, and the total probability is 1. So that's how you can convert this into probabilities. Now, when I say like low surprise, it's denotes with high probability. Okay, low surprise is high probability and less information. Okay, so being sunny, if someone tells it's going to be sunny here, it's low surprise because the probability of that happening is very high, and I have very less information to react. Okay, it's like take it for granted. Okay, there's nothing to be surprised about. So I know that it doesn't carry this statement doesn't carry any any information. If someone tells it's going to be sunny here, suppose if someone tells it's going to rain tomorrow, okay, then it's like I would say low. It's a medium surprise. Medium surprise. It's like medium probability. Okay, or I would say it's actually a low probability, but it's a medium probability, and it has got some information. Okay, so compared to these two, when somebody tells it's going to rain in Chennai, it's a medium surprise because it still rains, so it is not something like completely ruled out, but it's a medium surprise, and the probability of this occurring is like zero point 0.1 or 10%. It has some information. So now if you try to connect the dots, okay, and anything which is having low surprise and high probability has got less information. Anything which has got some surprise and some probability, which is not known, I mean like it's not in the higher range, has got some information. So if you wanted to quantify this into an information, this is what it is. Okay, so information is equal to it looks like it's an inverse of probability, but it is not exactly inverse of probability. Suppose, for example, in this case, let's say the zero point 0.9 is my probability. Okay, and the surprise, if I take 1 by zero point 0.9, okay, as the inverse of probability, okay, and then my information is very high actually. Sorry, I have some information here. Okay, so it doesn't work that way. So what we use is log probabilities. Okay, we convert that information into 1 by the probability of that happening. So which is equal to log 1 is 0. This is like log 1 minus log 0.9. Okay, so log 1 is 0 and log zero point 0.9 I think is 0.15. So minus 0.15. So this information here is like 0.15. Okay, so the information is here is 0.15. So in this case, the for this case, we take log of 1 by the probability. Probability of that rain happening is 0.1. So it's log 1 minus log 0.1. Okay, log 1 is 0, log 0.1 is minus 3.3 or something. So this becomes 3.32 or something. Okay, let me check the exact value. It should be 3.2. Yeah, 3.2. Yeah, 3.32. Okay, 3.32. So this is what the probabilities are translated to information. Okay, so if you see here, the amount of information this statement carries, that it's going to be sunny tomorrow, has just got 0.15 of information, and the statement that it is going to rain tomorrow, if somebody says it has got more information, that it is like 3.32. Okay, now when you try to I mean, yeah, this is the information. So information is in short is equal to minus of log probability of x. So this is log 1 by probability of x. This is probability of x. So if you take the p of x at the top, it will probably it will be represented like this, minus log p of x. This is the information. Okay. So what is information? Let's repeat. It is the amount of surprise. It is quantified into a number. Okay, if the surprise is less, the information is more. If the surprise is low, the information is high. Okay, so the surprise is low, the information is low. The surprise is medium, the information is something better than nothing. Okay, and suppose if somebody says it's going to snow. Okay, snow probability of snowing in Chennai is 0. Okay, it never happens. So what happens here in this case? Okay, it is like it becomes like high surprise. Okay, it is like 0 probability, or like it will never happen, and it has got a lot of information because oh my god, this will never happen. So let's check the information. The information becomes log of 1 by 0. Okay, this is probability of 0, and this becomes undefined or infinity, which means that I don't know how much of information this statement carries. It's extremely huge that there is no boundary to it, but because that event will never happen and it has got extreme information. Okay, that's what it means. Practically, it does not make any sense to have extreme information. It doesn't. It just tells that okay, it's not going to happen. That's it. So anything which varies between like low to medium probabilities is what we have come up with across in daily life, and the information can be quantified like this. Okay, this is the fundamental of information. Now let's move on. Okay, let's move on to something called average information. We got information. We will move on to average information. Okay. Before we move on to average information, let's understand what average is. Let's take three numbers: 4, 5, 6. If you want to average this, what do we do? We add these numbers and divide the total number of numbers. And becomes 15 by 3. The average is 5. This is what is an averages. So internally, what actually we are doing is we are trying to we are giving a probability of these three occurrences to be equal, which means that there is nothing that these three numbers are equally likely, so we assign equal probabilities to it. So what we actually do is we do this actually: 4 into the probability of the number, 5 into the probability of the number, 6 into the probability of the number. If we try to do this, calculate this, you will again get the same answer. The answer is going to be 5. So normally when you do an average, we assume equal probabilities to all the occurrences. Suppose if you want to find the average of marks of a particular student, we don't give priority to one subject. Okay, we assume that all subjects are equally. I mean, he is supposed to learn all subjects with equal probabilities, and that's the reason the average is always the total number of subjects. Okay, suppose if I say that the student his mom is a mathematician and the student's dad is a mathematician, okay, and his sister is also a mathematician, and now if I try to tell what is the, I mean, like, can I give equal probability for him to, I mean, score marks in mathematics compared to some other student whose parents are not equally qualified? The chances are low. But we do not do it normally. But I'm just giving you an intuition of how we kind of assume equal probabilities when we try to average. That's the reason it is divided by total number of subjects or total number of data points we have. Suppose if each data point has got its own probabilities, I mean, like in examples I said, like if a student surrounded by mathematicians in his home, more likely he might be having more probability to score high in mathematics. So we cannot assume that, okay, and divide by total number of subjects. Okay, in that case we might alter, like, okay, for other subjects he can score with, let's say, probability like zero point 0.5 or something. For mathematics alone he can score with probability of 0.9. Okay, so we don't use it practically, but I'm just telling you an intuition of how we assume that when taking averages all probabilities are equal. But if you wanted to assign weightages to each of the data points, the average might change. Okay. Now, why I'm saying this is how the average information or is calculated. So in the earlier example, I gave you an example of what is the probability of it is going to be sunny. Okay, it's always 0.9 in Chennai, and the probability of rain, it's 10%, it's 0.1. If you want to find the average information, what we do is we try to find and multiply the probability of that event. Okay, it's like 0.9 into the information that provides, that is log of 1 by probability of x plus probability of 0.1 plus into log of 1 by p of x. Okay, that is the average information is basically what I'm trying to say is that, right, like we do an average here, we give equal probabilities for each of the numbers and divide it. We are trying to give probabilities according to what the nature says. Okay, and it's going to be like 90% is rain in here, 10% is rain, and 90% is sunny, and 10% is rain. So the probabilities are, I mean, assigned to each of those variables or values, and then we calculate the information which we did already, and we multiply it here. So in case what this is like probability of this is probability of sunny actually. Okay, we can call it probability of sunny. This is probability of rains. So this is like 0.9 into, we calculated that the information for being sunny is 0.15 in the previous slide. Okay, plus the probability of rain is 0.1, and we multiply with the information that the rain provides, that is 3.32. Okay, so this is the average information. Okay, so information is this part of this portion of the equation, that is nothing but your inverse of your log probabilities, which we calculated. And if you sum the I mean, if you average all the information, you get what you call an average information, and this average information is what you call it as an entropy. Okay, so entropy is nothing but your average information. Average information is add all the information and average it according to the probabilities. So this is given by sum of all the points. Here it is like y is equal to 1 to n. There are two probabilities. The probability of the event occurring, that is this, into the probability of 1 by log probability of 1 by probability of x. This is the equation of entropy. This is what we did. Entropy is nothing but the average information. What is our information? This is information. What we are doing is trying to multiply it with its probabilities and try to sum it. Okay, that's what is called as entropy. So what we have seen is information, and we have also seen entropy. Entropy is average information. Entropy is also known in a different form in physics. Okay, about how the motion of the particles, something like that, which we will not, which probably is not directly related to this, which you're talking about. This talks about the information entropy. Okay, so this is how you calculate entropy, and the log which you take here is log to the base 2. Okay, because it is a binary in most of the computer. If it's in computer science, you store things in binaries. So we use log to the base 2. So log to the base 2 is what is calculated here. Okay, so you would erase this again and just keep this formula for entropy here. Okay, I will write it at the top. This is information. I is equal to, this is the formula for information, and the formula for entropy, which we derived, is equal to sum of I is equal to 1 to n, sum of all the probability of it into log 1 by probability of x. Okay, this is the easiest way to remember it, because you multiply basically the probabilities with the information and sum it out. Okay, if you take the probability to the top, it becomes minus log p of x. That is another way to write it. So minus summation of p of x, or like log p of x, log p of x into p of x. So this is how you might see it in textbooks, but this is better to remember. It is easy to understand. So this is what is the connection between information and entropy. Okay, and I'll just repeat why we are using log here. Suppose, just to make sure that why we are not just using inverse, we are using log. Suppose if we toss a coin, okay, the coin is always having heads, and you know that the coin is a biased coin; it always has heads. Okay, and the probability of the heads is, probability of x is always 1, because it's a coin which is always biased and it's always going to give heads. Now, like anything which is known and is always going to happen. Okay, if you try to just inverse it, okay, it becomes 1 by 1. If you try to just inverse the probability, the information becomes again 1. Okay, what it really says is that there's nothing surprising here, but it gives me more information. If you do not use log, and if you just inverse the probabilities, because the probability, I mentioned that anything which is like high probability it should give you low information, right? High probability should give you low information. So here in this case, the probability of getting heads is high, because the coin is always going to throw heads, because it's a biased coin. And if I just inverse the probability, like 1 by the probability of getting it, I will get 1 as the answer, and this gives me high information, which is not the case. So that's the reason we try to use log, which if you try to do log of 1 by the probability of 1, what happens is this becomes log of 1 minus log of 1. Okay, using the log, or you can take it there. Log of 1 is 0, log of 1 is 0. So now the information becomes in 0. Okay, so which means that if there are multiple, if there is a biased coin and it is always going to throw heads, there is no surprise in it that it is going to throw heads. The information is 0. Okay. Now, if I wanted to find, we will extend this idea of entropy using the coins as well. Okay. Now let's say, this is again, I'm going to give one more example for its average information. Okay, using coin tosses. So the probability of getting heads and probability of getting tails. Let's assume that it's a fair coin. Okay, so heads is 1 by 2 and tails is 1 by 2. So let's plug in the values here. So if you want to find the information or entropy, average information of this not, I mean, a coin which is not biased, entropy becomes probability of heads, that is probability of heads, into log of 1 by probability of 1 by 1 by 2. Okay, that's what it becomes. Okay, so, or you can write it as 0.5. Okay, 0.5. Okay, and plus this is for we need to take one summation of all probabilities, right? This is for heads, and we do it for tails. So we get like again 1 by 2 log 1 by 2 is like 0.5. Now, if you try to calculate the entropy here, again we take it as 0.5 and into log 1 minus log 0.5 plus this is again 0.5 into log 1 minus log 0.5. If you see here, this becomes log 1 becomes 0, log 0.5 is 0.5 minus 0.5, so this becomes plus, so 0.5 into 0.5. Sorry, log 0.5 becomes minus 1. Okay, minus 1, this becomes 0.5, and here also it's like 0.5 into log 1 is 0, log 0.5 is minus 1, so minus into minus plus, so this becomes again 0.5. So the total entropy of a fair coin is 0.5 plus 0.5, which is 1. So if you wanted to kind of graph it, it becomes like this actually. Probability of the fair coin. If the coin is biased, which means that if it is having only only heads or tails, the entropy will be 0. Okay, and if it is like having a bias, I mean if it's not biased, the probability will be the entropy will be 1. So let's say its entropy is denoted by h, the entropy is 1. Okay, this value is 1. Okay, so the probabilities of being this is the probability of x is equal to x, which you can take heads or tails. And if you see the sum of the entropy of the coin is highest when it is when the probabilities are even. Suppose if the coin is biased, let's say it can take like 0.8 and 0.2. Let's say the heads becomes heads. Let's say it takes 90% of the time it is heads and 10% of the time it is tails. Okay, so what happens is the information total entropy will be different here, because the properties have changed here. We assume the properties are equal. If you just substitute 0.9 here and 0.1 here, and if you try to calculate it, we might get the probability of this. Okay, the probability of the we may get the entropy of this little different. Okay, that's how the entropy changes when the probability distribution changes between heads and tails. Okay, this is an example, another example of using information and the probabilities to calculate the average information, that is called entropy. Okay, now this is widely used in machine learning. We'll see examples of where it is used. Okay, now we'll extend this idea. Okay. Now we have seen information, we have seen entropy. Okay, now let's say you wanted to compare two distributions. Let's say you wanted to compare a distribution like where it is 0.9 and 0.1. Okay, let's say the probability of getting the heads is 0.9 and the probability of getting tails is 0.1. This is your true distribution. Okay, let's call it as P. The true distribution in the sense this is your coin. Okay, this is your coin, and you know that this coin is biased, and it always gives 90% of the time heads and 10% of the time it gives tails. This is what you know. And there is another distribution which is Q. Okay, and that let's say this is a model which you build, and that the output of the model says the probabilities of getting heads is 0.5 and the probability of getting tails is 0.5. So which means that this is your true distribution. That is, you know that this is how your coin is biased coin, but you're trying to build a model which predicts that okay, both the coins are equally probable and the probability distribution is 0.5. So what we are eventually trying to find out is are these two distributions the same? If the two distributions are the same, which means that you have built a model in such a way that it represents the true distribution, and your error is very less. If there is a lot of if the output of your distribution is different, whereas the actual distribution is this, then which means that there is an error, we need to correct it. So this comparison of two distribution is what we call it as cross entropy. Okay, and I mean there is an exact term, okay, which I'll tell you, which is called KL divergence, okay, of P and Q, okay, which is KL divergence of P and Q, which is equal to cross entropy minus entropy. Okay. Now we have seen entropy. We will see what is cross entropy, and then we will see what is tail divergence. Okay. Basically, trying to compare two distribution. If you visually see this, you can find that these two distributions are different. Okay. So you can say that okay, P is having distribution 0.9 with probability of heads and 0.1 probability of tails, whereas here the probability of heads is 0.5, tails is 0.5. And looking at the bars, you can tell that visually tell that these are different distributions. So how do you mathematically compare this? That is where this cross entropy and entropy and information everything will come and help us. So let's there are two terms here. Entropy, we saw what it is. This is what it is here. Now what is cross entropy? Cross entropy, you denote it like this. That is the information between P and Q. Okay, the cross entropy is between P and Q, which means you are trying to find the entropy P with respect to Q. So the only change in this formula is it is a version of entropy. So we'll again it can will take all the values between 1 to n, that is two trials, sorry, not two trials, two events, heads and tails. And the probability here it is P, okay, P of x, because P with respect to Q, and here you will use Q. Okay. Here instead of the probability of P, you will use probability of Q. So it means that you are trying to compare this distribution with this. So we are trying to use P here, that is coming from this distribution, and Q here, that is coming from this distribution. This is what is called as cross entropy. Now if you calculate the same entropy, this is cross entropy. If you try to calculate it here, what is probability of x? This is 0.9 here. We just calculated. P of x is 0.9. And what is the probability of q of x? It's 0.5. So P of x into, let's just separate it. It's like log 1 minus log 0.5, because q of x is 0.5, first value, plus 0.1, because 0. Comes from P of x, because it's P of x. P of 0.1 into log 1 minus log 0.5. Okay, so log 1 minus log 0.5, log 1 minus log 0.5, it comes from this term, that is q. And this P comes from this term, that is your original distribution. You're trying to compare this with this. This is the true distribution, which you know that when you toss a coin, it's always biased, and it always gets 90% of the time heads and 10% of the time tails. And you have built a machine learning model where the output says the probabilities of getting head is 0.5 and 0.5. You are trying to compare whether the output is exactly matching with the true distribution or not. So when you try to do this, you will end up having a formula which you kind of very similar to the entropy, where instead of P here you just use Q. Okay, that's the only difference between the entropy and cross entropy. Because you're trying to cross, find cross between these two, and trying to find the difference between these two. Okay, so the true distribution and the predicted distribution. This is true distribution. This is predicted distribution. Okay, now if you see here, what the value we receive is, let's log 1 is 0, log of 0.5 is -1. Okay, and here is log 1 is 0, log of 0.5 is -1, so this becomes 1. Okay, this also becomes 1. So 0.9 into 1 is 1. Again, the entropy is again here is equal to 1. Okay, the entropy here is 1 if you just calculate it. Sorry, the cross entropy here is 1. So we know that we have calculated the cross entropy to be 1. Okay, and Yeah, let me erase this and make some space, and we'll come back. Yeah, before I erase, I thought we'll repeat it one more time because it's difficult to kind of rewrite everything. So we'll start again. We started with the idea of information. The information is the inverse of probabilities, and if you take log to it, that becomes this both are same, that's information. Then we extended the average information, there is entropy, we're just trying to average the information with assigning probabilities based upon each distribution, and we have average information here, and we calculate entropy. And this is entropy between if you calculate the entropy between two distributions P and Q, that is called cross entropy, and it's between P and Q. The cross entropy which we calculated here is between the probability of P into log of 1 by the probability of Q, okay, this P and Q. The only change here is in normal entropy, this is both the same distribution. In cross entropy, where if you change the order, you need to change this actually. Okay, so that's which you need to be careful about what you're choosing it. So P here, Q here, P and Q. For this cross entropy, if you calculate it, the cross entropy of this is equal to 1, because very simple calculation, 0.9 into this, the probability is 0.9 into log 1 minus 0.5, log 0.5. Log 0.5 is zero point 0.5, sorry 1, minus 1, and if you multiply this minus, it becomes this becomes 1, and if you calculate this 0.9 into 1, this becomes 0.9, 0.1 into 0.1 becomes sorry 1 becomes 0.1, and if you sum both, the cross entropy is 1. Okay, so I'm going to erase this, the cross entropy is 1. So we will erase this and keep it. The cross entropy for these two is equal to 1. Okay, now let's try to kind of find the entropy again once again, and we already did it, we'll just do it one more time. The entropy of what? Entropy of if you're trying to find between P and Q, this is the cross entropy between P and Q, and minus entropy of P. We are trying to find the entropy of P. Okay, the entropy of P. Okay, this is between P and Q. Okay, so we want to find the entropy of P. Let's do it here one more time. The same formula, P of x, that is 0.9. Okay, 0.9 into log of 1 minus log of 0.9. Okay, this is log of 0.9 plus 0.1 into log of 1 minus log of 0.1. Everything is to the base 2. Okay, so if you calculate this becomes 0.9 into log 1 is 0, log 0.9 is 0.15 plus 0.1 into this log 1 is 0, log of 0.1 is 3.32. Okay, if you try to sum this, it becomes 0. Let me use calculator. Okay, just all right, just make it little down. So this is, I just use calculator to calculate this, and if you find that the entropy becomes 0.467. Okay, this is this part, okay, the entropy of P. This is cross entropy between P and Q, that is this part, that is 1. Okay, now if you subtract entropy minus cross entropy, that's what this is entropy, this is cross entropy. If you subtract, what you call it as we get 0.531 nats. That's what KL divergence, the unit of KL divergence. So if you wanted to find the KL divergence between the points P and Q, okay, and we use cross entropy and entropy. Okay, entropy is straightforward, we found it here. Just cross entropy, just one trick here. Just use to you just need to multiply the two distributions probability with the log probability of the predicted distribution. That's the only thing. If you do that, you will get both the quantities, entropy and cross entropy, and if you subtract it, you will get the KL divergence. Now you found out why we are using this. As I mentioned, we are trying to compare between your two distribution and the predicted distribution. So in machine learning, you always try to predict something and try to find how close is it to your original data. And if there is a problem, you try to kind of reduce the difference between these two. So what eventually happening is the learning process is trying to reduce the error between these two distributions. So eventually, when P and Q are or close, which means that you try to predict it correctly and learn it correctly, this distribution should come like this. Okay, this should become 0.9 and this should become 0.1. This is like 100% match. Probably there will be some error, so probably if you get like close to 0.8 or like 0.89 or point 0, I mean like point 10 something like it's kind of close to this, but 0.9 or something, but it kind of, but this is the idea, right? You got it, right? So you're trying to make a predicted distribution closer to distribution, and the learning process is trying to bring the distance between these two as small as possible, and we use cross entropy entropy to kind of get this, and this is all related to the information and information theory. Okay, so yeah, I think if you try to compare the difference between two entropies, that becomes information gain. In decision trees, you will try to kind of do some splits. Okay, let's say you have data like this. Let's say you have points between like triangles and rectangles, and sorry, circles and rectangles, and you want to try and make a decision to split this. You find the entropy of this, and you find the entropy of this. If the entropy is, if the probabilities of getting, basically you're trying to split the classes in such a way that there is no mix in it. If there is a mix in it, it becomes, that's what we call it as impure classes. And we use information gain to kind of, that's nothing but your different entropies to kind of figure out whether you're able to split it correctly. Suppose if the split is like this, okay, which means that you have not split it correctly because you have a mix of both classes in both the places, and decision tree is not, this tree is not a very good tree to kind of split this. So this is how information gain and information theory is all related to kind of machine learning. Okay, thank you.